I'm Casey. I've helped a lot with the Ethereum JS team. So last year, getting Ethereum JS up to Byzantium compatibility, where Byzantium was the most recent fork. And I've also helped a lot with fuzz testing. So using fuzz testing to find all the consensus bugs before Byzantium was activated. And I'm not going to talk, well, the point isn't to talk about formal verification. More the point is to sort of get the options between unit testing and all the way to formal verification. I'm not an expert in formal verification, but without further ado, excuse me. It's like open and. Well, you're just missing a video. That's fine. So the EVM is a stack machine, and every bug that we find, or whether it's a bug in the client or a bug in the contract, the point is that the stack machine is not working as intended. And if you don't know what a stack machine is, then this video would have showed you. But the 3 gets pushed onto the stack. This blue circle is the stack. So the 3 gets pushed first, then the 2 gets pushed on top. Then the program counter moves over to the add, and the 2 gets popped off, the 3 gets popped off. They get added by the interpreter. The result is 5. The 5 gets pushed back onto the stack, and then it gets returned. So hopefully you understand what a stack is now. Might be a little important later. So the 2 types of bugs we're trying to find are bugs in clients and bugs in contracts. So let's talk about bugs in clients first. So consensus bugs means that one client is correct and another one is not correct. The other one has a bug. It's not really a big deal to the average user. It's only a concern that keeps you awake at night if you're either a client developer or an exchange operator, because, well, if you're an exchange operator, it could potentially be used to steal Ether from you, and if you're a client developer, then you'll have to wake up in the middle of the night if one of these bugs is found. And this happened in Thanksgiving 2016. And so the next time around, Thanksgiving 2016, were some denial of service. There were some DOS hard forks, Spears Dragon and Tangerine Whistle. And before those releases, the clients were not fuzz tested. So we wanted to try to prevent the same thing from happening for the next fork, and so we started fuzzing. The type of bugs that fuzz testing can not detect is when it's the same bug in all the clients. If you have an executable specification like KEVM, then you could potentially detect it because it's sort of a correct reference implementation so that you can fuzz test against. But without that, if all the clients were incorrect, then that is like the worst thing that you can imagine. I mean, so a consensus bug is actually not that bad because at least you know about it right when it happens, but an implementation bug that's present in all the clients, that's a horrible nightmare because you may not know until days later that it happened. And we've never had one of these except prior to the launch of the mainnet, and even that is only hypothetical if Geth was the only client. Bugs in contracts, you have bugs in contract code if the person writing the Solidity made a mistake, or bugs in compiler code if the people who wrote the Solidity compiler made a mistake. So types of testing. Unit testing, everybody probably understands. You have to write your test cases one by one, and we spent a lot of time doing this for Byzantium. Thinking hard. Oh, what types of edge cases can we create? What weird sequences of opcodes would be unexpected and might be untested, and everybody working on Byzantium sort of tried to think up test cases, and then once we thought we had thought of them all, then it was sort of, okay, let's go on and get ready to activate the fork. Fuzz testing, these unit tests are automatically generated. So you can run your fuzz tester for a week or for a month, depending how much time you have, and see if you find any bugs. You can also formally verify stuff. We'll get into that later. An important one that is often overlooked is the integration testing. So a couple failures of integration testing, the Wi-Fi crack attack. It was formally verified. It was mathematically proven to be secure. But there was still a vulnerability because the assumptions that under which it was formally verified did not match up with the actual production environment. You could do a hypothetical example for the parity, the second parity wallet bug. Yeah, maybe it's secure if you do everything right, but if you forget to call init wallet, then it's not. Yeah, so like I said, for Byzantium, we did a lot of unit testing. They are called state tests and blockchain tests, and they're run by a multi-client black box test runner called Hive. One thing we were worried about before the activation of Byzantium was the block difficulty formula, because the way the clients ran these unit tests is that they could only accept a unit test where the block number started at 0, which meant we couldn't actually test the difficulty formula unless each client maintainer implemented a custom unit test runner, which very few of them did, or almost none of them did. So we just crossed our fingers that there was no, bug in the difficulty formula, or rather the implementation of the formula in each client, and luckily there wasn't. So better than unit testing is fuzz testing. You blast it with a lot of different inputs. Fuzz testing has found a lot of bugs in a lot of projects. But of course, there's multiple kinds of fuzz testing. So the common fuzzing, like these bugs here in Firefox, Internet Explorer, Flash, etc. Majority of those are found with common fuzzing. So it's just an input trying to find a crash. With the Ethereum clients, I don't think we didn't find a single, well, we did find a couple of crashes, but we found even more bugs where the input didn't cause a crash. So if we were just doing common fuzzing, then we wouldn't have found these consensus bugs. So how we find them is with differential fuzzing or equivalence testing. So we, execute one contract. We generate a contract, run it on Geth, run it on Parity, run it on CPP Ethereum. If there's any difference, then it's a consensus bug. So how do we generate these contracts? We have two ways. One is with heuristics-based or targeted fuzzing. You manually write your own custom test generation logic. So you have to be clever, and you have to say, oh, well, maybe if we do like a call, stop. I mean, so it's similar to the mental process when you're handwriting unit tests, except you just write that in code and then sort of add some probabilities to get a bunch of random combinations. Then the other way is coverage driven. So you instrument the code base, and the first coverage driven fuzz tester, AFL, it was a big advance because prior to that, the best, the fuzz testers that found the most bugs were the ones that had the most clever heuristics for generating these test cases. But coverage-driven, it works out of the box on any piece of software that can, whose code coverage can be instrumented, and it automatically discovers the tricky inputs that that developers would come up with, but it comes up with them automatically, and it works out of the box on any piece of software that you apply it to. Some caveats about fuzz testing. You're not going to find all the bugs. Because you never know if you found all the code pass. So just to be clear, the difference between code coverage and code pass. Code coverage is the usual metric you'll see on like GitHub coveralls. Oh, you have 89% code coverage. Okay, we got 100% code coverage. If you have 100% code coverage, does that mean you have no bugs? No. It just means you're hitting every line in the code. It doesn't mean that you're hitting every possible path between lines in the code. So if you hit every possible path between lines, then yeah, then in theory there are no bugs. But you don't know the total number of paths unless you formally verify it. So, and also you may not discover paths that depend on very specific inputs. Okay, so the fuzz testers we use are a custom version of libfuzzer, which is a LLVM thing. So yeah, Guido Vranken created that. EVM Lab, which our head of security Martin Swendy had started, and TestEth, which Dimitri maintains. It has a one of these custom test case generators with heuristics. So this is the code that generates a random, a sequence of bytecode that should be correct. So we run that, and we compare the traces between each client. So here, this is a trace, and this, you can see here that this thing on the far side is the stack, and it grows with each push. So here's here's FB being pushed on the stack. Here's 0 being pushed on the stack, CB being pushed on the stack, 2DD, so forth, until boom, these two exclamation points mean that parity got a different result than Geth and C+ and CPP Ethereum and Pi Ethereum, and the difference was this last number on the stack, where all the other clients got a 0, but parity got an FB. And that was actually the first Byzantium consensus bug. So that's EVM Lab. It's using our custom written test case generator. Then we also have the coverage-driven client fuzzer, which uses code coverage to automatically discover interesting inputs. So the coverage-driven one inserts these coverage statements, like fuzz helper add coverage. So in every conditional, every branch, and that's how it measures the code coverage, at least for the Go code. Yeah, So one thing I did with the fuzz testing was get all the traces aligned for coming from each different client, and it was a lot of work, and I was afraid it was going to be a waste of time because some estimates were that, how much would you bet that there's going to be a bug in, a consensus bug in Byzantium, after it's released, or even before it's released, as we were leading up to it, and some estimates were like, maybe 30% chance that, that there's a consensus bug. And we put all this work into the fuzz tester, getting the, the traces to be standardized, and then we ended up finding 7, 8, consensus bugs, not just one. And so it's unfortunate that, developers can't write correct code on the first try. But I was glad that all the work on the fuzz tester, didn't turn out to be a waste of time. So moving on to property-based testing, and towards towards formal verification. Property-based testing, you're generating random inputs and you're testing that whatever property you write. So regular fuzz testing is you're testing that it doesn't crash or that all of the outputs are the same. With traditional property-based testing, you have to write a custom test generator, and more recently, there are projects that include a coverage-driven test generator, so you don't have to do that. But we did all this work on fuzz testing the EVM, so we started wondering, well, how can we fuzz test contracts? Idea: you execute an instrumented EVM, measure the path coverage over the bytecode, and then what do you check? Well, when you're testing the clients, you can just easily check, okay, make sure that all the clients have the same output. When you're testing a contract, it's not so clear what you're supposed to test. Another option, if you write multiple versions of your contract, then you can, check that all of them are equivalent. Okay, so that's one relatively easy way out. Because if you have to write your preconditions, your postconditions, your invariants, it's not so obvious what those should be. But you kind of have to do that if you want to fuzz test. So the question is, if it's basically equivalent to a specification. So if I have to write a specification in order to fuzz test it, then why shouldn't I just go ahead and do formal verification? Well, good question. Maybe you should. Many tools for formal verification use symbolic execution. Let's see how much time I've got here. 10 minutes. And so what they do is they transform a program into this giant Boolean formula and brute force it to check that there's no no way to falsify that formula against the preconditions, the invariants that you have specified. You don't have to write it in OCaml or Haskell. You can formally verify Python code. Uh, and indeed, some of the tools for verifying EVM code is written in Python. So Oyente, with Oyente you can verify certain properties because they have pre-written the specifications for you. So they've written the properties or the invariants to guarantee that there's no call stack depth vulnerability, that there's no reentry vulnerability, that there's no timestamp dependency. And you can see that in the when you run Oyente, you get the green check mark. Yeah, there's no call stack depth. Yeah, there's no reentry. Yeah, there's no timestamp dependency. And so you're just digging into the Oyente code. You can see how it imports Z3 and uses Z3 to power the this process of guaranteeing that those things can happen. With KEVM, you write your own custom properties, for your applications, and you have to specify those properties. The hard part is that the specification is in a pretty low-level language. So here's an example, specification. I think this is just like, the first part, above the fold, and below that, maybe it's even more complicated. But yeah, so if you want to formally verify something, you have to write a bunch of stuff like this, describing what your application should and should not do. So needless to say, it's not the easiest thing in the world. It doesn't really, the things that work out of the box are just the generic specifications that are pre-written for you, okay? But if you have to write your own specification, and that's, it's like a whole new ball game. And it might be just as difficult, to write a correct implementation in the first place. And if there, yeah, there might be a bug in the verifier. If you're going to put, $1 billion in the contract, then maybe, use multiple formal verifiers and hope they don't all have the same bug. So another type of formal verification is, so Y3 was the initial one in Solidity. They removed Y3. Now it's now they've added a similar thing. It's called an SMT checker. In these invariants are they're easier to write because you can just write them in Solidity, and they'll look like asserts that you're used to if you write unit tests. But they won't catch bugs in the. But if there's a bug in the Solidity compiler, then you won't know. So it could still, in practice, be incorrect and be vulnerable to losing money. But you won't know. So people talk about a formal spec of the EVM. The main one we have now is KEVM. The yellow paper it's semi-formal because it's not executable. You can't actually use it in any of these mechanical proving tools, whereas KEVM you can. Oops. And I cannot see that. Okay, here we go. What's up? This is not my laptop.
There was no keynote on the Mac. It doesn't work.
I'll just go over here, try it.
It doesn't work. Want to finish?
Okay, summary. If you don't write a full specification, at least write some asserts, and if you don't write the asserts, if you don't write any asserts, then write a couple implementations. Yep. Just come find me if you want to tell me I was wrong or have any questions.